The test is next week's Tuesday. The syllabus for the test is up to and including directional derivatives. So already we're into stuff that's not in the test. Excuse me. We're quite far ahead of mainstream, which in fact it is the plan that we're ahead of them. We have 5 lectures to their 4 lectures, so we do get ahead. And that allows us to slow down when we get to things like surface integrals, when we get to things like Green's and Stokes and divergence theorem. So that by the time we get to the end, we're back in step again. However, I think that they're a little bit further behind than normal, because usually we've got up to double integrals by now. So yeah, I hope they're not going to struggle at the end of the semester, but that's not our problem. I'm sure they will solve that problem by themselves. So the syllabus for the test is up to and including directional derivatives. It's next week, Tuesday evening, from 6 o'clock until 7:15. I have been told what our venues are, but I can't remember them. I'll put them up on Vula. It's more than one venue, because we're a big class. There'll be an alphabetical split. Oh, excuse me, sorry, I have a frog in my throat this morning. Okay, let's carry on. So yesterday, we showed, that, please keep quiet, if z is equal to f of xy, the gradient vector at any point, could you please keep quiet, is orthogonal to the level curve passing through that point. Okay, and I sort of illustrated what that's talking about by drawing a hill, okay, with the level curves drawn onto the hill like contour paths on a mountain. Okay, and then the level curves get drawn on an xy plane. And here we've got a point on the one level curve. Its projection is over there. And the gradient vector is orthogonal to the tangent line passing through that point on the level curve picture. Because if z is a function of 2 variables, then there's only 2 possible derivatives we can do, the x derivative and the y derivative. So when we cluster them together into a vector, it's necessarily a 2-component vector, and hence we draw it on a 2-dimensional picture, the level curve picture. Okay? So it's orthogonal to, so even though that information came from a surface, the level curves themselves are curves on a 2-dimensional picture, if you will, and the gradient vector is a 2-dimensional vector. Okay, so what I'm going to do is I'm going to step this up a dimension. So similarly, it can be shown that grad f is orthogonal to any tangent vector at a point on a surface. If S is a surface, I'm using a capital. So basically what I'm doing here is I'm taking a surface equation. So think of any surface equation, a sphere, a cone, anything, some surface equation. Instead of writing it as z equals a function of x and y, bring all the variables over to one side of the equal sign and think of it in terms of something involving x, y, and z equaling a constant. And if we do that, we can think of that surface as being a level surface of a higher dimensional surface analog. So just like level curves we'd get by taking our z equals f of x, y, and taking our z and replacing it with a constant. Now we've got a function of x and y equals a constant. That's a curve. So if you take your surface, you cluster all the variables together on one side of the equal sign, and you write it as something involving x, y, and z equaling a constant, you can think of it as a level surface of a four-dimensional object, where we don't actually bother with thinking about what that four-dimensional object is. We just think about that level surface and the properties that correspond, or not correspond exactly, the properties of level curves now have corresponding properties for level surfaces. If S is a surface that looks like that, and P is a point with 3 coordinates, is a point on S, then for any curve, I'm writing it as a space curve, parametrized space curve, passing through P, we have the grad of F. Now, my big F is a function of 3 variables, so it's going to have 3 derivatives, so it's a 3-dimensional vector. But we're going to end up with the same sort of geometric property, if you will, of the gradient vector being orthogonal to any curve that happens to pass through the point. So basically, we end up with, just like in that level curve picture that's at the top of the page there, at the top of the screen, that black arrow was orthogonal to that purple curve. We're now going to be getting arrows, if you will, orthogonal to surfaces. Okay, so think of a thorn sticking out of a cactus. It's sticking out orthogonally. If grad F is orthogonal to a surface, it follows that it can be used as the normal, as a normal perhaps, of the tangent plane. If it in fact even has a tangent plane, in other words, if f is differentiable. And so we end up with the x derivative. So you know when you have a plane, you have ax plus by plus cz equals d. Here my a, b, and c will be my 3 partial derivatives. So my x partial derivative times x minus x naught plus my y partial derivative times y minus y naught plus my z partial derivative times z minus z naught equals 0. And that's the equation of my tangent plane. So, at a basic computational level, given a surface, you can either make z the subject, and then you have z equals some function of x and y, and you can work out a 2-dimensional gradient vector, which if you wanted to draw it, you'd have to draw it on a 2-dimensional picture, and the thing that it's orthogonal to will be level curves. But instead of actually making z the subject, another option, just at a basic computational level, is to keep all the x, y's, and z's, all the variables on the same side of the equal sign. Constant don't matter, they can be anywhere, because we're just going to differentiate. Think of that expression with the x's, y's, and z's. Think of it as a function of 3 variables. Work out the gradient vector of that function of 3 variables, which will necessarily be a 3-component function. So if you were going to draw it, you wouldn't draw it on a 2-dimensional picture, you draw it on a 3-dimensional picture. And the thing that it's orthogonal to is no longer level curves, but level surfaces. In other words, your surface that you started with. Okay, so that might sound like a lot of words, and some of them quite complicated words, but it's quite an easy idea. Fundamentally, you get a gradient vector, and that gradient vector is orthogonal to your surface. And because it's orthogonal to your surface, you can use it as a normal to your tangent plane. Question?
Can we use the same method that we were using yesterday, just step it up 1 dimension?
Yeah. Okay. In the special case, now sometimes in your surface equations it's quite tricky to make Z the subject, but usually in our typical surfaces it's quite easy. So in our typical surfaces, which I'm going to call a special case, in the special case, where we can make Z the subject, we have, okay, if we can make Z the subject, it must be possible to take this function of x, y, and z and to actually write it as a function just of x, y. So basically, think of it going the other way. Think of starting with z equals f of x, y, and then taking z across the equal sign, so you get f of x, y minus z. And it's that f of x, y minus z that we're choosing to write as big F. Okay? If we now work out grad of big F, it's going to be our x derivative of little f. Let me not be sloppy here. Let me be precise. The x derivative of big F will be the same as the x derivative of little f. The y derivative of big F will be the same as the y derivative of little f. And the z derivative of big F will be minus 1. So if you're choosing to recognize those three components of grad big F as your a, b, and c of your plane equation, you get little f of x times x minus x naught plus a y derivative of little f. Oops. Okay, where the z derivative is just minus 1. And then if I let z minus z naught be the subject of the equation, we end up back at the formula that we had a couple of days ago. There should be little noughts in there. I'm leaving out my naught subscripts. I shouldn't in this particular case. Which is the formula we saw earlier. And if you don't recognize it, go back in your notes about today's question. Not in the special case where big F can be expressed as little f minus z, because little f won't have any z's in it, it'll only have x's and y's in it. It's a special case, as I say.
What do you mean by special case?
Where you can take your big F and you're able to tease apart the terms so that z is all by itself and the other terms are just x and y, which you have to be able to do if it's possible to make z the subject. As I say, think of it going the other way. If we'd actually started with z equals some function of x, y, and then we'd taken z across, and then we'd chosen to call that big F. Okay, so what's the bottom line here? The bottom line here is you can use your partial derivatives to get your tangent plane. And you have two options of how to do that. You can either just solve for your x and y derivatives and use the formula that's at the bottom of the screen there, which we have encountered about 2 days ago. It's the slightly less general formula because it does require that we can make z the subject. Now, frankly, we usually can make z the subject. So even though it's not a particularly general formula, it's usually applicable to our needs. However, the more general formula is the one that's up there near the top of the screen, where you don't need to make z the subject. You just have all your x's and y's and z's all together in one basket. You work out your x, your y, your z derivatives of that whole shebang, and you make those your coefficients of the tangent plane. And it's all because your gradient vector is orthogonal to your surface. Yes?
If you're dealing with a special case and you use the top formula, we still get the same.
Oh, absolutely. So the question was, if you have a special case and you use the top formula, would you, you would get the same formula, yeah. So, let's have a look. Should I demonstrate? What do I have lined up? Sure. I'm still asleep this morning. My head is full of fog. Hopefully I don't say anything silly. I'm busy setting the TUT test for this afternoon and tomorrow, and there was one question I did wrong 4 times. I'm actually going to show it to a colleague before I give it to you, so she can just check that I can actually still differentiate. I'm pretty sure I can differentiate, but my evidence this morning is not strong. Syllabus for the TUT test, which doesn't really narrow it down very much, is tangent planes, chain rule, and directional derivatives. But that's what the TUT is on, so that's not a surprise. Okay, I'm sure there's something I want to do. 127 according to my notes. 127. Okay, I'm going to demonstrate with exercise 127. I'm at the bottom of a page, so I'm just going to do a page jump. Oh, it's black. Let's go back to purple. Please keep quiet. Okay? Let capital F of x, y, z equal x, no, there's no brackets, silly me, equal xy plus 2yz minus xz squared. Plus 10, sure, whatever, I don't care about the constants, I only care about the variables. So you can put the plus 10 in there if you want, or you can think of the plus 10 as going across the equal sign and then we're only taking what's left. I'm only interested in the variables. Poor old constants, nobody cares about them. Oh dear, sometimes they're very important, but not right now. Y minus z squared, derivative with respect to y, x plus 2z, derivative with respect to z, 2yz minus 2xz. Okay, let's determine grad f at the point minus 5, 5, 1. And it is 5 minus 1, which is 4. Minus 5 plus minus 2. Minus 5 minus 2. Plus 2. Jeez. See, I can't even do arithmetic, let alone calculus. X is minus 5 and Z is 1. So it's minus 5 plus 2 is minus 3. I can do this. 2yz, that's 10 plus 10. Somebody tell me I'm right. I clearly need affirmation. Here we go. 127, 127, 127. 4 minus 320. I agree with my solutions. That's always nice. Yes, question over there somewhere. Yes. I'm not seeing us talking. There we go. Second last line. How? Okay, if you could please keep quiet. But there's another question, so let me just take the question in case it's related, yes? Okay, all right. Let's if everybody keep quiet, I'll explain, and possibly I've made mistakes along the way, so I'll let me double check my work at the same time. So first of all, I defined big F as all the variable stuff in that first expression. I think we're okay with that. And then I'm working out grad of big F by working out the 3 partial derivatives, the x partial derivative, the y partial derivative, and the z partial derivative, and it's entirely possible with my foggy head today that I've made a mistake. So let's walk through it. First of all, I want to differentiate with respect to x, so it'll be y minus z squared, because the 2yz doesn't contribute to the x derivative. As far as x is concerned, that's just a funny looking constant. Okay, now the y derivative, it'll be x plus 2z. Yes, and the xz squared doesn't contribute. And then the z derivative, now it's the turn of the first term to not contribute, and it's 2y minus 2xz. Just 2y. You're right, it's just 2y. There we go. Does that affect my... No, it doesn't, because the z was only 1 anyway, so my actual numeric answer is still correct. Are we all on the agreement now? Yes, I should just copy blindly from my solutions today. Okay, 4x minus 3y. Well, let's have a look. We want 4x plus 5 minus 3y minus 5 plus 20z minus 1. I often just write the 4x minus 3y plus the 20z equals, and then I figure out what the constant's supposed to be. But there we go. 4x minus 3y plus 20z equals, let's see if Tracy can do arithmetic, 20 plus 15, that's 35, and then minus 20, so back down to 15. Have I got a minus 15 over there? I do. Have a look. Let's have a look. Did I go wrong? That's a minus 20. It's a 5. That's a plus 15. It's 20. Have I putting in the wrong signs? 20 plus 15 minus 20. Might be really dim in my solutions. It's minus 15, but surely it's plus 15. Oh, right, of course, it is plus 15, but then you take it across the equal sign, right? Oh my goodness, I should just take the day off. Right, I think I need a donut or something. Okay, all right. Is there anything else I need to torture you with today while I slowly make arithmetic errors? Okay, all right. Let's try 128. Please keep quiet. And I shall rely heavily on my solutions, which hopefully I typed up on a slightly brighter day. Find the equation of the tangent line. Oh dear, this looks hard. To the curve of intersection of z equals 5x squared plus 8y squared. And the other surface is 2x squared plus 3y squared plus 1 minus z equals 0. And they've given me the points. Okay, now we know how to do that. How do you find a curve of intersection? Well, let's look. I have two, what are those? Those are both elliptical paraboloids. One's a happy elliptical paraboloid, the other one's also, in fact, a happy elliptical paraboloid. Oh, interesting. Okay, if one had been happy and the other one sad, I would have been convinced that my curve of intersection was a Pringle curve of some kind. But with both of them as happy paraboloids, it becomes a little bit more ambiguous what the curve of intersection is going to be, but I'm sure we'll find out. You'll see in the question it says two different methods. The second one, the parametric equations ones, that's the one that we'll already be familiar with. What would I do there? I would eliminate z. I'd make z the subject of both and then make them equal to one another. I'll get something involving an x squared plus a y squared with random constants. And I'd parameterize that using cos and sine. And then I'd plug that back into either of those two surfaces to get my z. Boom, I've got my c, my curve of intersection. And what they're wanting is the tangent line, so that I'll work out my r dash, etc. I'll get my tangent line. That's method B. Method A says using gradients. Okay, so here I'm going to draw a rather funny looking picture. Let's have a look. I'm not interested in... let's assume we've got, I'm just trying to show the basic idea. Let's say we've got two surfaces that intersect in some curve. So here's the curve, and this curve is my curve C, and this is surface 1, and this is surface 2. And I want to use gradients to find, well, not so much my curve of intersection, but the tangent line to the curve of intersection. If at a particular point I find the gradient vector to the one surface, grad of S2, and I find they look like they are orthogonal to one another. They're not supposed to look orthogonal to one another. Let me try and redraw that picture. They're supposed to look orthogonal to their respective surfaces. So let me retry. Grad S2 orthogonal to S2, and then I'm going to draw grad S1, which is orthogonal to S1. Sorry, that's rather scruffy notation. I wouldn't call it Yeah, okay, that's scruffy notation, but I hope you follow. If I then take those two, so the curve of intersection lies on the one surface, but it also lies on the other surface. So because grad, the two grads are orthogonal to the two surfaces, it means if I cross them, I'll find a vector that actually lies along the curve. Cross the two grads, two is spelled T-W-O, not T-O-W, here we go, T grads, to get the tangent vector. Okay, then while that might not be crystal clear right now, I hope if you stop and think about it for 5 minutes, you'll agree. The tangent vector of the curve has to be orthogonal to each of the grads, because the tangent vector of the curve lies on the surface, or it lies on the tangent plane at that point. So it's orthogonal to the one grad, it's also orthogonal to the other grad, so if I cross the two grads, I'll get a vector going in the right direction. Okay. Yes, question?
If our two surfaces are just in terms of x, y, and z, and not in terms of a parameter like direction, then when we cross S1, S2, and S1, S2, S1, we get two opposite directions. How do we know which one is the correct direction?
Okay, so if you cross those two, your curve of intersection doesn't really care, and your tangent line doesn't care. So yes, you're right. If you cross the two gradients one way or you cross them the other way, you'll get two parallel vectors, but not the same one. You'll get one will be going in the exactly opposite direction to the other, and it doesn't matter. They're both acceptable for the purposes to which we're putting it. So let my one function be 5x squared plus 8y squared minus z. Remember, you've got to bring all the variables together. Yes, question?
Could you please go through that diagram again?
Okay. Let me write this down. 3y squared minus z. Let me try and demonstrate with something. Problem is everything's so flat-edged in this class. It would be nice if we had something that was kind of round. Okay, all right. So imagine you've got, so I'm just going to draw it in the air with my hands. Imagine you've got some sort of curvy surface, okay? And you've got some other sort of curvy surface, and they're intersecting in some curve, okay? So they're intersecting in a curve, all right? Everywhere all over the first surface, the gradient vector is orthogonal to it. You can almost think of it as little thorns that are pointing out of it, okay? Or like one of those deep-sea fish with the spikes. And on the other surface as well. So we're particularly interested in where those two surfaces meet. So those two surfaces meet along some curve, all right? At a particular point on that curve, if we zoom in, the tangent vector along the line is lying along the curve. Well, I mean, it's tangent to the curve, but if we just zoom in on that point, that tangent vector as we zoom in is lying on the surface. Or it's lying, strictly speaking, on the tangent plane to the surface at that point. But just think about zooming in. Effectively, it's lying on the surface. So because it's lying on surface 1, it must be orthogonal to the gradient to surface 1, because the gradient is orthogonal to the surface. So any vector that's lying on the surface must be orthogonal to the grad. But simultaneously, that tangent vector is orthogonal to the other grad, because it's lying on the other surface as well, so it must be orthogonal to the other gradient. So the tangent vector, which is what I'm looking for, is orthogonal to gradient 1. It's also orthogonal to gradient 2. So if I cross the two gradients, I will get a vector that's orthogonal to both the things that I was crossing, and hence is parallel to the tangent vector. So it's kind of subtle, but there you go. Just trying to think, I know there's something in first year vector geometry where you do something similar. Where is it? Oh, yes, in fact, exactly the same thing, but you do it with the intersection of two planes. If you intersect two planes and you cross their normals, you'll find the direction vector along the line of intersection, which basically is exactly what we're doing here. It's just we're not just dealing with planes. Okay, so let's work out grad of big F. I'm a big squash for place. I'm going to leave out the bracket x, y, z, and I'm just going to copy it from my notes, because clearly differentiating is just too hard for me today. Okay, so you simply work out the x, y, and z derivatives of your big F and your big G. I'm going to specifically find them at the point in question, which is 1 over root 3, 0, 5 over 3. Oops, too many brackets. Oh, what do we got here? 10 over root 3, and 0 and minus 1. Cool, that's not too bad. And the G, over root 3, is that right? Yes. And 0 again, and minus 1. And then you cross them. You cross those two vectors using whichever method makes your heart happy. It's not too bad, there's lots of zeros, so that always makes it a little easier. Let's see if I can still manage something as demanding as chain rule. Here we go, grad F. Okay, I'm just going to call that, because I don't want to keep writing. I'm going to call that V1, vector 1, and I'm going to call that vector 2. V1 crossed with V2 is, right, let's have a go. That's 0, subtract 0. And it's minus 4 over root 3, add 10 over root 3. Minus 4, add 10 is 6. And then that's 0, subtract 0. Oh, okay. And 6, of course, is 2 times 3, so I could cancel out that root 3 and just get... That's the same thing. It's the same thing, because if you take the 2 times 3 at the top, you can think of 3 as root 3 times root 3 and simplify. Okay, so the tangent line is going to be x of lambda equals the point. We were given the point right at the beginning, and I've gone past it. There we go, 1 over root 3, 0, 5 over 3 plus lambda 0 to root 3, 0. Okay, all right. Let me quickly do method B. Method B is using parametric equations, which is, yeah, I suppose it's a fairly vague instruction, but I know what they mean. They mean 5x squared plus 8y squared equals, let me make z the subject, 2x squared plus 3y squared plus 1. So let's tidy that up. That'll be 3x squared plus 5y squared equals 1. Okay, so I'm wanting 3x squared to be cos squared theta, and I'm wanting 5y squared to be sine squared theta. So x is going to have to be 1 over root 3 cos t. Let me use t rather than theta. Doesn't matter. Y is going to be 1 over root 5 sine t. And z is therefore going to be whatever I get if I plug those back in. And so I'm not going to do that. Doesn't matter which of your surface equations you substitute your x and y back into, you should get the same result for z. If you don't, it means you've made a mistake. Because the whole point is we're trying to find something that's common to both. And what does it come out as? It comes out as 5 over 3 cos squared t. Oh, that's just a... Sorry, that went a bit funny. Just I'll go back and fix that. Scroll up to the previous method. You okay with that? Okay, all right. All right, so that's parametric equation. So that's my R. I'd need to work out R dash and evaluate it at t. Okay, let's have a look. What was my point? My point, sorry, I realize we're getting towards the end of the class, but we're also getting to the end of the problem, so that's fine. What value of t will give me that point? 0? Yeah, t equals 0. Okay, take your time doing that, particularly since triggers involved. Because sometimes different values of t will still give you the same value of cos, but there's only one specific value of t we really want, so just take it a little bit slowly. Okay, so that's our r. Our r dash of t we'll get just by differentiating. Okay, I'm running out of time, so I'm actually just going to leave that line blank. I'll fill it in when I save it to PDF, but I don't have time right now. But once you plug in your t value, you end up getting 0, 1 over root 5, 0. So when you draw up your tangent line, you end up with something that looks like this. Okay, and then you might look at that and go, oh my goodness, but that's different to what we got in part A. Because in part A we had, our middle component was 2 root 3. But remember that all we want for the direction vector of the line is any vector that runs along the line. There are infinitely many vectors that run along the line, and they are all scalar multiples of one another. So the fact that the answer A gave us 0, some number 0, and this one is also giving us 0, some number 0, means they are scalar multiples of one another. If you take 1, you just need to multiply it by something, and you can turn it into this one. So they're still describing the same line, even though they're using a slightly different direction vector to do so. Okay, we're at the end of the period. I'll stop now.